Hey guys, welcome back to video 5. Today we're going to be calculating our last portfolio in this section, which is going to be a portfolio that maximizes the certainty equivalence for an investor given a specific risk aversion. So I'm going to be posting a video fully dedicated to risk aversion in the portfolio theory section. So if you're unfamiliar with how it's calculated and where it's derived from, I just quickly review those concepts. So we're going to assume the investor to have a power utility function and therefore a constant relative risk aversion. And two economists, Pratt and Arrow, have showed that the certainty equivalence can be represented with this formula, where the certainty equivalence is equal to the expected return minus 0.5 times A, which is your relative risk aversion, multiplied times the variance of the portfolio. So we're going to start by looking at the two asset case for a certainty equivalence formula, because when we start to get to N assets, the math really gets a bit hairy, and these tutorials have probably had too much math anyways. So when we break out this certainty equivalence formula here, we ultimately get that the return is equal to a weighted average between the two assets, and then it's subtracted by half times A times just the typical formula for the variance of a portfolio, especially with two assets. And when we take the derivative with respect to W and set it equal to 0, we ultimately can solve for W star, which will give us this equation. So now I think it's important to understand the intuition behind this certainty equivalence formula for the optimal weights. So let's think about stock E or asset E as having more variance. Then the optimal certainty equivalence is going to start to drift away from this minimum variance portfolio weights in a two asset case. If one, the risk aversion is lower, meaning A, or the denominator is lower, or B, the stock's variance, it has a higher return premium, meaning this numerator here is higher, or there's a lower variance between D and E. And if any of those three cases are in fact true, then the optimal weight is going to be added to this specific asset within that vector. So now let's return to Python and code this into our portfolio for an N asset case. We start by assigning the variable GAM equal to 4, which is going to represent our relative risk aversion. So the next thing is to calculate the optimal vector of weights. And we think about this as starting with the global minimum variance portfolio weights. And then we're subtracting asset weights based on the inverted covariance matrix multiplied by our mu vector of return from the 47 industries, and subtracting from that the return on the global minimum variance portfolio that is then scaled by someone's relative risk aversion. So if we go ahead and calculate the return as we always do, which is the weights just times mu vec, we should see that its return is higher than the global MVP. I went ahead and calculated the standard deviation of the portfolio because we've done this calculation about 10 times already. It's just the transpose vector of weights multiplied by the covariance matrix multiplied by the vector of weights, and then just take the standard deviation of it. So now that we have all of our portfolio statistics, we're ready to add this certainty equivalence portfolio to our plot. So we're going to go ahead and copy this plot code down, and all we need to do is the same thing we've done so far, is just adding the portfolio statistics to our existing scatter plot. So we're going to add sig r to the x-axis, and then we'll add mu r to the y-axis, and then we're just going to want to add text as well. And the only thing here is you need to change the variable names from our tangency to our certainty equivalence portfolio. And let's call this portfolio R. And if we execute this code, you should see that our portfolio R has been plotted. And it's a reasonable result because we're building off the global MVP weights. So we have a relatively higher return from the global MVP based on the individual's risk aversion. So now we plotted all 5 or 6 of our portfolios, but we don't really know their performance relative to each other based on statistics. So our next job is to, export a table that's going to allow us to look at the means, the standard deviations, and the Sharpe ratios of each of these portfolios. So we can then compare their performance in sample and then going forward out of sample through 2014 through 2019. Now we're going to put these mean, standard deviations, and Sharpe ratios into a table so we can properly compare the portfolios. So we're going to start by assigning the variable D is equal to these curly brackets. And in Python, a curly bracket denotes a dictionary. And dictionary is just a data structure that maps one value to another. So right now we're mapping this portfolio to these values or characters that we're going to call these portfolios names, your G, E, M, M1, tangent C, and R. So that's going to be one column. And then next we're going to map the value mean, and then we're going to say that's equal to, or use a colon to say that's equal to brackets, and then we're going to put in our means for our 5 portfolios. Finally, we're going to put these dictionary values into a data frame. So we're going to assign the variable df is equal to pd.dataframe, or pandas data frame, and just it's cap sensitive, so be careful. And our first argument is going to be data, and we're going to set that equal to d, or the dictionary values we just had. And the final step is to round. So we're going to set, again, the variable df, or the data frame we just made, is equal to df.round, and we're going to round to 2 digits. And if we execute this code and return the value, we should see our portfolio statistics. And just taking a quick look at here, we see that the standard deviation of the global MVP is the lowest by design within this group of portfolios we have. And the tangent C portfolio also has the highest risk-adjusted return, or Sharpe ratio, by design. And you can see that all of our optimized portfolios here have higher Sharpe ratios than our unoptimized, equally weighted, and market portfolios. So the next step, or in the next video, we're going to apply these optimized portfolios to periods that weren't included in the sample. So we'll look at 2014, and then we'll look at 2014 to 2016 and see if these optimized portfolios still are really beating the unoptimized portfolios of the equally weighted and the market portfolio. I hope to see you guys there.